So in the early 30s, Pascal Jordan, John von Neumann, and Eugene Wigner were formalizing the mathematical bedrock of quantum mechanics. And the entire framework relied on things called observables.
Observables, like things we can actually measure.
Exactly. Things like momentum or spin. But since our audience is pretty familiar with the physics here, we know observables aren't just simple scalar numbers. They are represented by Hermitian matrices.
Right, which are basically grids of complex numbers with very specific symmetry properties.
Yes. And the crucial property being that the eigenvalues of these Hermitian matrices, the actual outputs, are always real numbers.
Which is absolutely mandatory. Because, I mean, if you measure the momentum of a particle in a lab, your instrument reads out a real number.
Right, exactly.
You cannot get a complex number with an imaginary component on a radar gun. It just doesn't make physical sense.
It doesn't. That is the physical constraint anchoring the math. Real measurements need real numbers.
Okay, so where does it break down? If they had this grid system, why did the math suddenly stop working?
Well, the mathematical framework allowed you to add two observables together, or multiply an observable by a real number. So if you take two Hermitian matrices and add them, the result is always another Hermitian matrix.
Meaning the system is closed under addition, the math guarantees a physical reality?
Exactly, but the glitch emerges when you need to multiply them.
Uh-oh.
Yeah. If I have observable A and observable B, and I want to calculate a state that requires multiplying matrix A by matrix B, the resulting matrix is almost never Hermitian. It loses that crucial symmetry.
Wait, okay, let's unpack this for a second. It's like if you're a baker mixing two physical ingredients together, like flour and sugar, but instead of getting dough, you get, like, the abstract concept of Tuesday.
That is exactly what it feels like mathematically. It just breaks the rules of reality.
Right, because suddenly its eigenvalues are complex numbers.
Yes. The standard operation of matrix multiplication spits out an unphysical result. If you input two physical measurements, the system outputs an imaginary state that cannot exist in reality.
So the math was essentially telling von Neumann, Wigner, and Jordan that the quantum universe was not mathematically closed.
Precisely. And that is a fatal flaw for a physical theory. If you can't combine fundamental properties without generating nonsense, your theory is broken.
So what do? Did they just throw matrix mechanics in the trash?
No, rather than abandoning it altogether, Pascal Jordan decided the problem was standard multiplication itself. So he rewrote the operation.
He just changed how multiplication works.
He did. He introduced what we now call the Jordan product.
Okay, how does that work?
Well, instead of simply calculating A times B, he created a symmetrized operation. Essentially, you calculate the matrix product of A times B, then you calculate B times A, you add those two resulting matrices together, and then you divide the whole thing by 2.
Oh, wow, so you're basically averaging the two directions of multiplication.
Exactly. It is a very elegant brute force solution. By forcing the combination of A and B to be perfectly symmetrical, the resulting matrix retains its Hermitian properties.
So it guarantees the eigenvalues remain real. You input two physical observables, run them through this new Jordan product, and you output a third physical observable.
Yes. The game keeps running. It saves the closure of the physical system.
Okay, but, and I feel like there's a big but, coming here, mathematical patches of this magnitude always carry a systemic cost.
Well, a massive cost. By defining this new product, Jordan stripped the algebra of a foundational property. He sacrificed associativity.
Wow, okay. This is where things get truly counterintuitive.
Yeah.
Because associativity is the grouping rule, right?
Right.
Like if you were operating on three elements, A, B, and C, associativity guarantees that combining A and B first and then combining that result with C is exactly identical to combining B and C first and then combining with A.
It is the absolute bedrock of predictable algebraic structures. But under Jordan's symmetrized product, that rule dissolves completely. Grouping entirely changes the final mathematical outcome.
Wait, so the order in which you evaluate the system alters the physical state you were trying to describe.
Yes.
But wait, if grouping is broken, how does this mathematical house of cards stay standing? Doesn't breaking a rule that fundamental ruin everything else? Like, how do you even define a cubed?
You've zeroed in on the exact reason they couldn't just leave the algebra completely unconstrained.
Because evaluating the expected values of squared operators is non-negotiable for calculating standard deviations or uncertainty in quantum mechanics, right?
Exactly. If A times A is ambiguous, depending on how you group it, the Heisenberg uncertainty principle would mathematically disintegrate.
Which we definitely don't want.
Right. So they had to inject a strict compromise into the rulebook. They allowed general associativity to die, but they demanded a highly specific safeguard. It's a concept called power associativity.
Ah, power associativity,
It-
also known as the Jordan identity, right? It acts as like the minimal viable constraint.
Yes. The Jordan identity is an axiom enforcing that, while mixing different observables like A, B, and C creates non-associative chaos. Multiplying a single observable by itself repeatedly must remain predictable.
So if you take observable A, square it using the Jordan product, and then combine it with A again, it will yield the exact same result no matter how you group the term.
Exactly. The power of a single state is mathematically protected.
So they basically engineered a Frankenstein structure.
It's a great way to put it.
It's not associative globally to force physical closure, but power associative locally to allow for variance and probability calculations.
Right. And once von Neumann, Wigner, and Jordan built this machinery, their instinct as mathematicians just took over. They immediately sought to classify every possible version of what they termed formally real Jordan algebras.
They wanted to map the entire theoretical landscape of this weird new algebra.
They systematically analyzed how many distinct mathematical spaces could exist that obey the commutative but non-associative Jordan product while strictly adhering to the Jordan identity.
Now, usually, mathematical classification theorems yield infinite families. Right. Like if you classify regular polygons, you find triangles, squares, pentagons, and that sequence extends to infinity.
Sure.
Even with highly complex structures like simple Lie algebras, we find 4 infinite families. I would assume their classification of Jordan algebras uncovered a similar endless sequence of variations. I mean, math has endless possibilities.
They did find infinite families, yes, but they discovered a harsh divide in the taxonomy. The structures cleanly split into 2 categories, special and exceptional.
Okay, special and exceptional, let's break those down. The special Jordan algebras form an infinite family, right?
Right. And they're considered special because despite utilizing the strained symmetrized Jordan product, they can always be secretly embedded back into a standard associative matrix algebra.
So they're essentially associative algebras in disguise. They use the non-associative rule, but you can neatly map their elements back onto familiar, well-behaved matrices without generating any contradictions.
Exactly. They are completely tame. You can analyze them using the traditional toolkit of associative mathematics.
Okay, so what about the exceptional ones?
The classification theorem revealed the second category, the exceptional Jordan algebras. These are the structures that fundamentally refuse to be embedded in any associative framework.
Oh, wow.
They are natively inherently non-associative all the way down to their core.
And this is the real bombshell of their 1934 paper. Because when they mapped out the exceptional category, they didn't find an infinite family, did they?
No, they didn't.
They didn't even find a handful. Out of all possible mathematical spaces spanning to infinity, they proved there is exactly one exceptional, formally real Jordan algebra.
A solitary mathematical singularity.
Just one. That is so wild. Out of all the possibilities, what is it called?
It is known as the Albert algebra, named after Abraham Adrian Albert, the mathematician who finalized the proof of its uniqueness.
Okay, we need to examine the anatomy of this singularity, because it's often described as a stray piece of operating plane from a different universe. To understand why it refuses to fit into standard mathematics, we have to look at its building blocks, right?
We do.
So, without getting bogged down in complex equations, the Albert algebra is basically a space of 3 by 3 matrices. But the entries inside those matrices aren't regular real numbers or even complex numbers. They are built from something called octonions.
Yes. The octonions are the key to the Albert algebra's isolation. We should trace how we arrive at them because it perfectly illustrates the degradation of algebraic properties.
Okay, let's go.
We build number systems using a mathematical doubling procedure called the Cayley-Dickson construction.
Right, so we start with the standard one-dimensional real numbers.
Exactly. And if we double them by adding an imaginary unit, we generate the 2-dimensional complex numbers.
But that doubling comes with a tax, right? We lose the property of ordering. Like, you can't definitively say one complex number is greater than another in the way you can with real numbers.
Precisely. Now, if we run the Cayley-Dickson process again, doubling the complex numbers, we get the 4-dimensional quaternions.
And the tax increases.
It does. We lose commutativity. With quaternions, A times B no longer equals B times A.
Which, by the way, is why quaternions are uniquely suited to calculate 3D rotations in video games and physics engines. Because the sequence of rotation physically matters.
Exactly. But if we push the engine one more time, doubling the quaternions, we reach the 8-dimensional octonions.
Here's where it gets really interesting.
Yes, because the tax for this 8-dimensional space is the complete loss of associativity. The building blocks themselves lose the grouping rule. X times Y times Z does not equal X times Y times Z.
And that is where the road effectively ends for quantum physics, isn't it?
It is, because if you try to double the octonions to generate the 16-dimensional sedenions, you encounter zero divisors.
Meaning you can multiply two non-zero numbers and just get zero.
Right, which completely breaks the mathematical property of division. And without a division algebra, you cannot define quantum probabilities.
So the octonions are the absolute frontier of mathematically viable number systems. They're these wild, rebellious building blocks. And the Albert algebra takes these inherently non-associative 8-dimensional numbers and arranges them into a 3x3 grid.
Yes. And because a 3x3 matrix has 3 degrees of freedom on the diagonal and 3 distinct octonionic entries off the diagonal, which are 8-dimensional each, the entire structure balloons into a massive 27-dimensional space.
27 dimensions. And because it is built from octonions, its non-associativity isn't just a byproduct of Jordan's clever physics patch. It is baked right into the fundamental coordinates of the space itself.
That is why it cannot be embedded into any standard math. It is natively alien. Furthermore, the 3x3 matrix is the absolute maximum size this structure can tolerate.
Wait, really? What happens if you make it bigger?
If you attempt to build a 4x4 matrix out of octonions, the Jordan identity fails entirely. Power associativity collapses.
Oh, wow. So you couldn't even predict squaring an observable anymore. It is heavily constrained.
Very much so.
We have this one isolated 27-dimensional mutant structure built out of rebellious 8-dimensional numbers. A mathematical island that cannot be expanded, cannot be embedded, and stands completely alone.
Right.
But, a theoretical object is only as valuable as its application. So does this freak of mathematics actually do anything, or is it just a trivia fact? Because for a long time, physicists assumed the Albert algebra was just a dead-end curiosity.
They did. But then the math started bleeding over into the study of pure symmetry. It turns out this single isolated algebra acts as the hidden scaffolding for the highest forms of continuous symmetry known to humanity.
You're talking about the exceptional Lie groups.
I am. Lie groups are continuous transformations. Think of rotating a sphere perfectly smoothly, where every infinitesimal shift maps the object back onto itself.
So the standard Lie groups describe the symmetries of familiar spaces, like the rotation group SU2 or SU3, or the rotation group SO3, which governs three-dimensional space and maps perfectly to the physics of angular momentum.
Exactly. But mathematicians discovered 5 exceptional Lie groups that describe symmetries of incredibly bizarre high-dimensional spaces, and the Albert algebra is the hidden linchpin driving them.
Let's look at the exceptional Lie group F4. It is this massive 52-dimensional symmetry group. For decades, it was really difficult to visualize what F4 actually operated on.
Right, but it turns out F4 is precisely the automorphism group of the Albert algebra.
Meaning F4 is essentially the exhaustive catalog of every possible way you can symmetrically transform, rotate, and manipulate the 27-dimensional Albert algebra without breaking its internal multiplication rules.
It is the exact geometric manifestation of that algebraic space. But the twist is the connection goes even deeper, moving from F4 into an even larger exceptional group called E6, which is 78-dimensional.
And this is achieved through another process called the TKK construction, right?
Yes.
The TKK construction developed by Titz, Cantor, and Kuchar. We often see this referenced in the sources as a bridge between Jordan algebras and Lie algebras, but how does the mechanism actually work? How do you leverage a 27-dimensional space to build a 78-dimensional symmetry group?
Well, the TKK construction is essentially a way of treating the algebra not just as a static space, but as an active set of transformations.
Okay.
Instead of just looking at the elements of the Albert algebra, you look at all the mathematical operations you can perform with those elements. You take the structural symmetries we just talked about, the F4 group, and you combine them with the operations of multiplying by the elements themselves.
Oh, I see. So you are binding the internal symmetries of the space together with the actual geometry of its mathematical operations.
Correct. By interlocking the space with the operators acting upon it, you mathematically synthesize a much larger Lie algebra. The Albert algebra undergoes the TKK construction and perfectly generates E6.
That is profound. This isolated mutant born from fixing a quantum physics glitch secretly encodes the DNA for the most complex symmetry structures in mathematics.
It really does. And when you start manipulating these high-dimensional symmetries, the geometric consequences are just staggering. Specifically, the Albert algebra dictates the coordinates of an exotic geometry known as the octonionic projective plane.
And this leads us to the failure of Desargues' theorem.
Yes, this is where the loss of associativity violently physically manifests. In standard projective geometry, Desargues' theorem is the bedrock of linear perspective.
Right. It dictates that if you project two triangles from a single central point Thor, like casting a shadow from a light source, the corresponding sides of those triangles will intersect, and those 3 points of intersection will always perfectly align on a single straight line.
It is the mathematical guarantee that converging lines in a perspective field will resolve in a predictable, linear manner. It is literally why a 3D rendering engine functions.
Right. But proving Desargues' theorem relies heavily on coordinate geometry. To prove that the lines intersect, you have to set up algebraic equations equating the coordinates of the points. And resolving those equations requires grouping the coordinate variables together, calculating a times b, and then multiplying by c.
And there is the fatal structural flaw. In the octonionic projective plane, the coordinates are octonions. They are non-associative. You mathematically cannot group A and B together and get the same result as grouping B and C.
So because the algebraic coordinate system forbids consistent grouping, the geometric proof just collapses.
The math literally prevents the lines from resolving at a shared coordinate. In the octonionic projective plane, the fundamental laws of perspective completely shatter.
That is wild.
The geometry is so deeply twisted by the underlying algebra that lines which should intersect simply glitch past one another.
It's basically a geometric landscape devoid of linear perspective, spawned directly by Pascal Jordan's attempt to fix matrix multiplication. It's fascinating how the abstract algebraic weirdness directly creates geometric weirdness.
It's all connected.
But I want to pivot back to reality for a moment to ground this for you. We've spent a lot of time in 27-dimensional octonionic space. Did the tame cousins, the special Jordan algebras, ever find practical utility today, or were they completely overshadowed by the exceptional one?
Oh, the special Jordan algebras actually became highly instrumental, but in fields utterly disconnected from quantum mechanics.
Wait, really? Like what?
Because they are grounded in the symmetrized Jordan product, what order doesn't matter, but power associativity ensures consistency over time, they map perfectly onto systems driven by symmetric recombination. The most prominent example is actually population genetics.
Oh, wow. Population genetics. Okay, that makes perfect logical sense. When analyzing the inheritance of traits, the biological mechanism is natively symmetrical.
Exactly.
If a biological offspring receives allele X from the paternal line and allele Y from the maternal line, the resulting genetic combination is strictly identical to receiving allele Y from the paternal line and allele X from the maternal line.
Right. The genetic sequence doesn't care about the order of input. XY equals YX. Biologists utilize these complex statistical frameworks called gametic and zygotic algebras to track how these gene frequencies distribute and stabilize over generations across large populations.
And because you are calculating distributions across multiple generations, you're essentially squaring or cubing the genetic probabilities over time. So you require a mathematical system that guarantees those generational powers behave predictably.
Which is the exact definition of power associativity.
That is so cool.
The statistical matrices tracking gene flow in population genetics often function as special Jordan algebras.
So the exact mathematical constraints von Neumann engineered to preserve the reality of a quantum electron in the 30s are currently being used to calculate stable trait distributions in, like, agricultural crops and epidemiological models.
Yes. It highlights how universal these structures really are. But, while mainstream physics largely abandoned Jordan algebras decades ago, the story isn't over for the exceptional side of the family either.
Right. Because the Albert algebra is currently making a massive comeback. at the very bleeding edge of speculative theoretical physics.
It is the unavoidable mathematical gravity of the structure.
Scientists are exploring if this unique structure might be the exact key needed to unify the force of gravity with the standard model of particle physics.
Right. The ultimate objective of modern theoretical physics is to reconcile general relativity, which operates on smooth, continuous space-time geometry, with the standard model of particle physics, which is governed by quantized, discrete symmetries.
Currently, the standard model utilizes three-gauge symmetry groups, right? U1 for electromagnetism, SU2 for the weak force, and SU3 for the strong nuclear force.
Correct. But gravity fundamentally refuses to mathematically merge with them. To unify them, string theorists, particularly those working in M-theory, utilize 11-dimensional frameworks.
And when they attempt to compactify those extra dimensions to arrive at the 4D spacetime we actually experience, the math requires overarching symmetry groups to dictate the behavior of the particles.
And this is exactly where E6 enters the chat. Grand unified theories frequently employ the Lie group E6 because its sheer size and complex substructure can naturally encapsulate the U1, SU2, and SU3 groups within its geometry.
It is a perfect theoretical container.
Exactly. And because we know the TKK construction dictates that E6 is fundamentally generated by the Albert algebra, physicists are analyzing the 27-dimensional representations of E6 to model new fermion generations.
So the non-associative octonionic bedrock of the Albert algebra might actually be the hidden mathematical scaffolding required to stabilize the interactions between gravity and quantum forces at the Planck scale.
That is the hope. It demonstrates that when we push the mathematical boundaries to patch a localized problem, we often uncover the universal engine.
Just to briefly recap this journey for you, we started with a broken calculation in 1930s quantum measurements. To fix it, physicists sacrificed basic math rules, which spawned a classification system that isolated a single 27-dimensional mathematical exception.
Built entirely from abelious octonions.
Right, and that solitary algebra secretly governs ultimate symmetries, creates exotic geometries where perspective fails, and is now serving as the architecture for the unification of the cosmos.
It's an incredible full-circle moment.
Which presents a lingering, provocative thought for you to ponder on your own. If a mathematical patch, engineered somewhat arbitrarily by a human in 1934 to fix a local calculation error, inevitably perfectly describes the highest dimensional symmetries of the fundamental universe, are we inventing the math to suit our theories, or is the universe simply forcing us to stumble upon its native source code?